Hello everybody. If you're new, welcome. We are writing a kernel from scratch. Let's get started. Right, so last time we've worked on actually getting our APs started, and we actually did that. So we could check that they do get running, and we could count the number of APs that we have. So let's actually quickly just rerun our platform to see that it works. Right, so CPU count after wake up is 8 and before wake up is 1. So we had just the Bootstrap processor running, and then we had 7 new cores joining to share the fun. So before we continue on AP initialization, because we need to set up a stack for each of the cores, and we also need to, well, do pretty much all of these things, so descriptors, interrupts, and all the other things that we have already done for our Bootstrap processor. We need to do them for the APs also. But before we do that, I would like to go and deal with the IO Apic and interrupt routing. So that's what we are going to work on today. Right, so I have digged around and found this datasheet for this chip here, which is the IO Apic. Amazing specs and fairly recent. No, just kidding. So as is the norm for x64, we do have quite a lot of baggage, and we do need to handle quite a few things just for the sake of backwards compatibility, even though we don't really want to. This is one of those cases. So to explain, to simply explain how this IO Apic works, and by the way, this is a real chip, so you can see the actual pinout. This was actually available to buy by motherboard manufacturers who needed that. And so yeah, you did have the different packagings, and you could actually go ahead and order this. Right, so that's not what we are here for. What we are here for is this, and I'm going to try to explain this fairly quickly. So this is the IO Apic chip that we are talking about. It has these interrupt input pins, which are inputs. And well, it also has this IMRQ, but we are going to just ignore those. And it is attached to the ISA bus. So here through the ISA bus, as well as through the interrupt and RQ pins, this chip here gets signaled interrupts, right? Then this chip's main role is to decouple the interrupts and RQ's attribution here across the ISA bus and other devices from the actual interrupts that the processor can service, because, well, there's just a limited number of them, so we can't map them one-to-one, as well as to allow motherboard and other device manufacturers the flexibility to actually hard code some, or hard wire, in this case, some interrupts directly to the unit to simplify their designs. Right, so this here communicates with the processors through the system bus or Apic bus. Depends on which generation we're talking about. And then this processor here will receive that interrupt in the local Apic. Now, the main thing that this, or another main thing that this chip does, is it allows to route interrupts differently. So basically we can have a mapping table that basically has input and output, and it goes like, if we get interrupt 22 in the input, we can route it to some other interrupt in the output to the local Apic. So we can route it to interrupts, for example, 0x EE, right? And we can have this for all the number of interrupts. Each of these units, as we should have somewhere over here in the specs. Yeah, there we go. So it has 24 maximum programmable interrupts. And ISA stands for, I think, industry standard something, which is funny because it's not industry standard anymore, but we move. Right, so how does this work? Or rather, we don't care how it works. There's a bunch of technical details there for device manufacturers. We are going to skip those. We are just going to focus on the actual interaction with software. So the way it works is fairly simple. We have two registers, two memory mapped registers, IO regcell and IO win. Regcell is for registers select, and win is for window. Actually, it's written here, so that's pretty cool. How it works is that in regcell, we so this one is regcell. We put the offset of one of these registers that we want to talk to, so read or write to. So I say I want to write to ID. So here I'm just going to put the offset of ID, which is 0. And then here window, the window register will actually point. So it has, this is implementation specific. So I'm just going to do something that's makes sense. So it's going to point to the memory that has that ID thing, right? And then if we put in version, so here instead of ID, let's say we put in version, then this window here will actually point to where the version is. And when we write a double word, a U32 to the address of window, we will be writing to version, but we can't, so it's read-only, but same goes for reading from it, so it's read-only. So if we read a U32 from the address of W, we will actually be reading from the IO Apic version registers. Right, so amongst the other registers we have, or actually the most important one is this IO read table, which is the read direction table. It has 24 entries, so 0 to 23, and each entry is 64 bits. Except that, remember, we can only write in chunks of 32 bits, so we are going to need to double write this sucker here. Right, and here we have a description of all the registers, where they are mapped by default. So, but we are not going to take this. This is fairly old. They are talking about something that doesn't exist anymore. We are going to actually get that from IO Apic structure. So IO Apic address is the IO Apic we are going to, or the address we are going to be using for this IO Apic. Right, so that's how it is. Back to the Batmobile. Right, so let's go here. So I'm going to create IO Apic, a folder or directory, and then I'm just going to go ahead here and create ioapic.sig, which will be the main driver. Not sure if we are going to need that yet or not, but yeah, it's nice to have. So, okay, so here we need to do a few things first. Obviously, I've already went ahead and so ACPI events, and I have added this here. So IO Apic found event, as well as the interrupt source event, which I haven't talked about yet, but I am going to. So this IO Apic event found, or IO Apic found event only gives us the IO Apic address, the GSI base, and the ID of that IO Apic. And that's in line with what we have here in this table here. So IO Apic, the address, and the GSI. And since we don't actually know how many IO Apics we can get on each platform, we are going to need to handle any number of them. So, or we can do what I've already did, and we can just assume that we are going to only have so a fixed number of them, and then we fail if we go beyond that. So here I've already put in the simple code that gets IO Apic, checks that we are not above the number we've allocated. We could have allocated this dynamically, but no one cares. Like, really, no one cares. So yeah, we move. Yeah, so here I've just created an array, static array here. I've created an array list on top of that static array, so just so that we can push the IO Apics into the array without needing to check for nulls. And same here for interrupt source overrides. Just create an array with 255 or 256 possible overrides, and create an array list that just uses that, or a bounded array list that just uses a static array. So nothing magical there. What's going to be magical is that now we are going to need to go and initialize this whole thing. So ioepic.sig, and let's get started. So first of all, we need to create some sort of handler or manager for the Apic, some sort of encapsulating structure. So let's call it IO. So IO Apic. Sure, can live with this. So here we need to public function init, and this one here will take. So it needs to take something. It needs to take the address, right? As a U32, I think we're going to need to check this afterwards. Then we need to create the so we need GSI base, which is probably a U8. Need to check, and I guess that's all we are going to need. And then this here would need to return self. I'm just going to do IO Apic like this. Of course, it's not used for now. So here we are also going to have a public function init that this time takes in a IO Apic an S. So this one here would be a slice of, and if I go here, let me just bring this, probably not what I want to do. So let me just get this here. So the IO Apics is of this type here, IO Apic, and this IO Apic type is something I've defined here. Right. So this might be something I need to move though. Or probably not. So hold on, let's just move on, okay? So SMP is import smp.seg, yeah. And here we can just go ahead and do IO Apic, or rather smp.ioapic. This one here returns void, probably errors out somehow. Not sure. But yeah. So now we can actually, so how do we go about this? We're probably going to need to create a variable here, some sort of array that will hold our IOAPIC management stuff, or IOAPIC driver. Let's call this driver, just so that we know what we're doing. So drivers, this will be a sort of array, and I think I'm going to go with the same things we've already done. So this one, I'm going to import options, and then this will be options.max CPU of IOAPIC driver, sure, and this will be undefined times options max CPU, sure. That looks okay. So this one here would need a driver also. Yep. Okay. So now the idea here is to go through IOAPICs and get IOAPIC, and then from that, let's actually do something like this. I'm just going to go ahead and do drivers. Will be, and I guess I'm going to need, oops, all over the place today, stud, and here we can do stud array list of IOAPIC driver, so in it with a buffer, which is drivers buff, right? Okay, so here, let's go. We want to, so for each of the IOAPICs we have, we want to drivers.append bounded, right? And we want to append init with IOAPIC.address and IOAPIC.jsi base. Yeah, sounds good. And of course, this one here can fail, so we are going to try that. And actually, before we do that, we can actually go ahead and create that. So driver is .init of IOAPIC.address and IOAPIC.jsi base. And I'm just going to go here, do that, and set the driver. Right. So what I need to do now is just a sanity check. I'm just going to if driver dot I guess ID is different from IOAPIC.id, then we probably return an error. Let's call it ID mismatch. Sure. So that means that here we need a public function ID that would return a U8, I believe. Yeah, okay, that looks pretty good. That looks pretty good. So let's actually move on. So here, let me go to the documentation. Here we can see that the IO register select is at Apic base at offset 00, and our window register is at offset 10. So I guess we should probably do that. So how do we go about this? I guess we can just have a const. Yeah, we can just have a const here. So this one is register select offset is 0, and we can do window, what is it called? Just window offset, so window offset. This one is 10 hex, yes. And that means that now we need functions here. We need to private functions to read and write from a given register. So read takes in a register, which is an IO Apic. No, it's a register. And of course returns a U32. Yeah, okay, that's actually fine. And then we're going to do write, which takes a register, and a value, which is a U32, and returns void. Does this fail? I don't think it does, at least not for now. So here now we need to create this const register, which would be just an enum over. So how are our registers? Our registers are given here, and they go from 0 to 3F. So let's say a U8. Right. So here we need ID, which is 0. Version, I guess, which is 1. I need to double check this. Version is 1, yep. Arbitration ID is 2. So arb ID is 2. And here we need so 10 is the very first redirection entry, and I think we can compute the other ones by doing some clever math. Yep. So the redirection table 0 so has 64 bits, for which the first, the high, is it the high or the low? I think this one is the low 32 bits, and then this is the high 32 bits. So I guess if we have this I here, this index, we can do this index times 2 plus 0 to give us the low 32 bits for each redirection entry, and plus 1 to give us the high 32 bits. So if we take, for example, 2, that would be so 4 plus 10, that's 14. That's correct. And then 2 plus 10, 2 times 2 plus 10 plus 1, that's 15. So that's correct. So I'm not going to encode all of these. I'm just going to encode the first one, the root offset, and then we're going to probably compute the other ones from there. So redirection table. Whoops, this one is, I guess we could just write 16, or maybe we could change all of these to hex. No. Yep. Okay, so that works. Now let's try to go ahead and create these things here. So what we need to do for read is we need to get the register offset, right? So this one would be int from enum of reg. And then we need to right, so now we have another problem, because this address we're going to get here is a physical address. So we are going to need to actually map it. So here I'm just going to go and grab, so in Apic in Apic, I think we already have everything that we needed. So all of this, thank you. And now I'm just going to go ahead and create log is, instead log scoped to IO Apic. And actually, I'm just going to rename this to base address. Yeah. And I'm not sure we are going to need to keep the base address around. So I'm going to do IO Apic base is this. So now we need to pass it a page map also. Which would be, let me just go ahead and see it from this. So something like this, and here you can go ahead and do const memory is memory.seg. There you go. Done. This one here is base address, and then here we go ahead and do IO Apic base to address. We need the actually hold on. We have it here. Base address. Constants. Yeah, we have them. Constants.say. Right, so 28 down. This one is IO Apic base. So we still want it to be uncacheable, and we still want it to be read and write. So that's good. Right, so it's about time. I think we defined a few fields here. So base address. Let's call it base physical address U32. Base address a b adder. Sounds okay. I guess memory.p adder and GSI base a U8. Oops, it's not 8. Okay, so this here needs to return something now. So return. And here we need so base phys address is base adder. Base adder is IO Apic base, and GSI base is, well, GSI base. I think that covers all the things we need to do. No, we still have this to add, because this can fail. And I think that's pretty much all there is to it. So now we have the register offset. So let's create a pointer for that. So reg cell pointer is a pointer to U32, and we do pointer from int of. Right, so now all of these need to take in a self, which is an IO Apic driver. Same goes for here, so self IO Apic driver. And same goes here, so self IO Apic driver. Right, so this one here is self.base address. And I'm just going to go here actually and just make that There you go. So plus, oh, right, to adder, right, plus the reg, no, plus, so this one is a const, so reg select, register select offset, yeah, register select offset. Right, so hold on, let me just close this. So now that we have this pointer here, we are going to do reg select pointer, and we are going to write to that the offset of that register. And now we can probably do pretty much the same for so win pointer. This is also a pointer to const U32 this time, because we're not going to write from it. Just need to do window offset here, and then we return win pointer dot whatever value is there. And I guess here we can go ahead and just do 32, because we are still going to get that 32. So this one is return self.read ID. Cool. So right would be pretty much the same. So I think we can just whoops, there we go, and we can set that in here. So this one is the same. The only thing that changes here is that now this is an actual pointer to this, and instead of doing this, we do like something like that. Yeah, sounds pretty good. I think we are on the right track. Okay, so let's actually tie everything together here. So by going to CPU, so inside init core, here we have initialized the IO Apic and done quite a few things with the IO Apic. Here I'm going to also try init, or rather local Apic. So here I'm going to do the same, but for IO Apic. Sure, so I guess this one doesn't exist. We can make it exist by doing something like this. This one does something like this, and here we can try. And I guess here we need to const ioapic is import ioapic.sig. Sure. Actually, this is just a module. So yeah. So ioapic.sig.init. Here we need to pass it a slice to ioapics. Sounds about right. But we also need to pass it. Yeah, that's something we forgot to do. So memory.kernel vmem.impl. Yeah, not too happy with that, but I guess we are going to move. So page map is a pointer to virtual memory manager, I think is what we need. Is that page map manager? Okay, fine. So page map manager. Of course, this is not used anywhere because we need to pass it here. Page map. Now everybody should be happy, I think. So just check that this works. I think that's all we need. So let's actually go here and run this. And of course, we are going to get errors. So expected type slice of whatever. Oh, right. Okay. So I guess my bad. This is not what we. Whoops. This is not what we need to do. We need to pass it items. That should fix it. Right. So let's go up here and see. Literal is not a function. I think just need to type in this. It's sad because for this to work, this can only be an IO Apic driver. So, but I guess it fails before it gets to there. So yeah. Expected type U8 found U32 G-side base. You know what? I'm okay with that. I'm okay with U32, so let's get on board. What's the problem here? Cannot convert union payload type. Right? Right, okay. I see it. So try. Expect use 64 found memory.v address. U64 found memory.v address. Oh, okay. Oh, yeah. It's a v address, not a p address. What are we even doing here? Whoops. I just clicked that too soon. I think I did. So initializing. Oh, cool. IO Apic base. And that should be okay. So let's actually just go ahead and do this debug. Any and should probably do something like drivers dot items, and maybe try something like IO Apic drivers. Should only have one of those on this virtual machine, but yeah. Okay, so let's see. Yeah, so we only have one driver here with a GSI base of 0, and it's been correctly initialized to the correct value. So let's actually try to. So here we're already calling this ID function here that tries the read. But here's what I'm going to do. I'm going to also do probably after this const d is drivers at 0. This is just for tests. Sure. Write, and I'm going to write register ID. I'm going to write 2 to that. Of course, no, this doesn't fail, so it should be all right. And then here we are going to do log.debug. And we print the ID, something like this. And here we can do d.id. Oh. Oh, yeah. Okay. So let's see here if this also works. Yeah, it does not seem like it does. So why is that? So here I think we got told that we could write to the ID register, right? Oh, I see. So we need to actually write the ID fairly high up. So, okay. That also means that this here is false. This is wrong. So we need to move this down by 24. And then we can just pick so they give us about 4 bits. So yeah, just something like this. Okay, well, and so that means that now this here needs to be moved by 24 for it to be an actual correct value and for us to be able to read it back. Okay, no, so still print a big fat 0 here. So how come? What is the problem with this? So here we select the register and we write the offset we want to that. That should be 0. Yeah. And then we go ahead and write. Yeah, so I don't see where the problem is. Okay. That is kind of weird. So let's actually remove these for now. Yeah, let's get rid of this for now. Just get back the full field. And see. Okay, so we do get a bunch of stuff on the field. I'm just not sure why. So we're reading 32 bits from that field. And here we gain 33554432, which is kind of bizarre. Okay, just going to add a few things here. So how do we go about this? Log.debug reading and probably something like this. So here would be register, and this would be win pointer dot that, probably something like this too. Yeah. So win pointer something like this. And yep, that sounds pretty good. So let's build that and see. Right, so here we wrote this value here, we read it back, but what is this? So hold on, are you telling me that if I do this, I get the actual value I put in? No way. Okay, so it was just a conversion issue then. Actually, let me just get this back as binary. I just want to check something. Cool. So here we need to have, so 10. Yep, okay. Looks good. Looks good to me. It looks good to me. Now, why did our idea here not work? I guess that's the question. So we need to shift it, right shift it by 24, and then we end it with 0xf to just take the 4 bits that remain. So why is this not giving us 2? This is giving me 0. Why is that? Yeah, this is kind of weird. So I'm just going to do const id reg is self.read id, and I'm going to log that. So debug id reg is so in hex and in binary probably, and here I'm just going to write that twice. So id reg, and here we get that that id reg, and we shift it left by 24. Actually, hold on a minute. There's something I need to do. Something very important I need to do. So what did we call that? Assembly. This. Hold eternally. I'm going to explain why in a second. Const assembly is import assembly.say. So that's this exit. Yep. So when hitting this while true, I can feel the CPUs, or I can hear the cooling AIO on my computer actually spin up, because it's basically doing a busy wait, which is kind of funny. Actually, I'm not sure if I can show that. Hold on a minute. So I'm just going to remove this and rebuild. And I've opened BTOP here so we can take a look at what happens. And if I just let this go here, and now I can feel my CPUs actually burning, and you can see them all go into 100% because they're all running that while loop. And thankfully we've only used 8 of those, but yeah, it's funny. So let me put this back here, run this again, and see that now they actually stopped doing that. Yeah, so now they are actually halting, and halt is a power efficient state, so yeah, they're not actually doing as much. Cool. So yeah, that's very funny. Right, so where were we? We were over here. So we were checking for this. Right, so now we actually do get the 10 here. So hold on a minute. What is happening here? What's the difference between this and because I guess that if now I go ahead and do this, it should still work, right? Right, so it does still work. This one also still works. But why did it refuse to work earlier then? So let's add 0xf. That still works the same. Just going to do something here. Just going to build with this so we can find it in the assembly. Actually, let's just exit from here. So kernel, build, kernel 64, elf. Oh, yeah, okay. Calm down. And we are looking for IO Apic. There we go. So IO Apic driver.id. So how come we call read? Actually, let's start with just doing this. Self.read ID. This is the original version that we had. So this one returns 0. This one returns 0 here. Whereas the read and write functions here do actually return a correct value. Right, so if we go here, do that again. So IO Apic driver, IO Apic driver. There we go. So why is this not working? Okay, so I guess the read function got inlined here. Yeah, I'm not sure I understand the test here. So put this into here. We go to well, okay. Here we move 0 to RBX. What is this? To which we add 10, which is the offset we have. Oh, no, okay, fine. So RBX has this here is the pointer to, or rather is the address of the pointer to reg select here. So RBX, we move 10 to RBX, so that would be no, rather we write 10, which is rather 0, which is the register, the ID register, to the pointer pointed to by RBX, which is correct, which is what we do here on this line. And then we add to the value of that pointer 10, which is this offset here. And then we read from that. So hold on a minute, where were we? We were here. So we add to RBX this here. And not sure why they generated these test checks here, but we do have a jump we need to take. So we have 2 jumps we need to take. So one is to 36E, which is I'm thinking where we get the actual address. No, okay, no, so that's cast to null. Okay, so those are the actual checks. Right, so where were we? We were about here. Okay, so we get that pointer in RDI for some reason, which is, I guess, self. And yeah, okay, so fine, that's actually fine. Otherwise, we compared the, what is this, RIP plus whatever to 0. I guess that's some logger or something stuff. And we go ahead and do some more things. So I guess I'm just going to simplify this by removing the logging. I'm just going to make sure that it still outputs the same. Yep, still 0. So let's try this again. IO Apic driver. Okay, a lot cleaner now. So we get the pointer in RDI. We put that in RAX. And we check for, well, here checks we are going to skip alignment. So we put 0 in that address. So we write 0 to that pointer. We then add 10 to that. And then we move RAX plus, what is this? Okay, I think there's a problem with the code generation here. This is bad. So let's try to now get the actual thing here. So id reg and rebuild that. I'm going to leave this alone here so that we can check it afterwards. So let me just do dump. So the mintel, and then we want build kernel 64 of course with the less, and we look for Apic driver. Right, so this one still does the same thing here. It moves the pointer from RX plus 3, which is kind of weird. I'm not sure why that is. So I'm going to add this here. We have no alignment constraints. Yeah, I guess we have no alignment constraints for the right, because we don't know how that looks like. But we should, I mean, no, we should still be aligned, so this should not be the problem, actually. This should not be the problem. So let me just actually run this and see that. Right, so this one is still bad. So what is going on here? So I think I need to now add this. So to force it to actually use or actually read the ID reg value independently, and then yeah, so now we get the actual correct stuff. So if we run this again and go for Apic driver, so let's go through this again. So these are the checks. We put 0 in here, we add 10 to that. And then we do a bunch of stuff for the logger. And I guess somewhere we should still be moving stuff to EAX. Where is our EAX? Right. Right, so here we move RBX to EAX. And where does RBX come from? That's kind of weird, okay. So I see RDX here. Here we have the call to write the logger stuff. Here we, not sure what we're doing here, but okay. Then we move RBX to RDX, move RBX to RIX, and it goes on for a while. And then we move. Oh, hold on. So yeah, okay. This goes here. We shift 0x18, I think, is 24. Just going to check that quickly. Yep, that's 24. So here is the actual logic. So EBX is where it's at. So where are the actions we take on EBX? So I missed something here. No, actually, let's do EBX or BX. There we go. So we move right. So okay, so this is where I want to look. So this line here, we read the actual value in RIX to EBX, whereas here we read the value of RX plus 0.3. Why is that? There is a problem in the code generation here. There is a problem in the code generation, and I don't think it's just because if I remove this line here, the problem comes back. Right, so here let's remember this. EBX, we take RX, right? So let's read that again. So IO Apic driver. Yeah, the problem is back. And I'm not sure why that is. Because this here should be just a value. So I'm not sure why it decides to So I think I know why it decides to do that. It actually makes sense because if we want to read, if we have this value here which has 24 or 32 bits, and we want to read the third or the fourth byte, we could actually just move the reading head to the fourth byte. So that means that we need to shift the address to that byte. But that does not work here because we need to read, we need to do reads from memory mapped or memory aligned things. So I'm probably going to add here that this needs to be from an alignment of 0x10. And actually, could we just pre-compute the register select address to be so a pointer to U32 and window is a pointer to U32, and can we just pre-compute those here? Register select is pointer from int of base IO Apic base dot to adder plus something like this, and here we can do window is window offset. Okay, and that makes this just go away. Here we can do self dot just select. And this now goes away also. So this becomes self.window. Yeah, I'm going to need this self.window, self.window, just to make sure that we haven't broken anything. So same here, this goes away, replaced by this, and this actually goes away, replaced by self window. I'm just going to bring this back, self window, and yeah, same goes here. Right. Let's see. Okay, so I think that we still have the same problem, but at least the reading and the writing here look okay. So let me get rid of these two for now. So how come this guy decides that now they would just read a pointer that's not aligned? Huh. So let's try to add an align of 1 here. Let's try to see if we can force it to actually generate good code without doing this in assembly. Yeah, no. Should probably instead do something like so the pointer is 16 bytes a line, so would that force it to generate correct code? Or no? No, I guess not. Okay, fine. So let's see what it's doing here. So Apic, Apic driver, and it's still doing the same thing here. Pretty sure we can force it to, so hold on a minute. If I go here and I set this to no inline, yep, okay, no inline goes here. Okay, so this one does force it to actually generate the correct code because it can't merge the yeah. Yeah, so it's forced to actually do the right shift after we get the value instead of trying to be all clever about putting it into the address. Right. But I still don't totally get why we want to, or they're trying to do that, because if we were asking for a U8, I would understand that. But the fact that we are asking for a U32 here, is it possible to actually go around that problem? Okay, I'm thinking that this is way past what we set out to do for this video, but I need to know. So this one here is bad, and I'm guessing that it just ignored the fact that I forced the yeah, so it still went back to whatever it tried to do first. Right, so what are we going to do? How can I force it to... Because I would understand if this was a U8, that shifting a U8 by 24 and then ending it with this should still be the same thing as just going to the... so here we have U8, U8, U8 and U8 in an array. This would be... So reading this, shifting this by 24, and and taking whatever value that is equivalent to just reading from... so let's call this an array. It's equivalent from going to array of 3, right? So that's what we've seen they're doing. They go to offset, so array pointed to the array plus 3. So that's how this code is generated here. I think we can get Zig to generate the AIR or something. I'll take a look at what it thought this, or why I thought this would be a good idea, but I think I'm going to do that later. And there's one other trick I want to do. Let's see. Yay. I think this might actually work. Driver. Yes. This actually forced the compiler's hand to read from the actual pointer instead of doing whatever it wants. Right, so this one is fixed. I'm just going to remove the no line here. Just going to try to see that this also works without it. Okay, still works. Well, the more you know. I think I'm also going to go to Apic and down in write register here, just going to add volatile. I'm just doing this to avoid this whole debacle. I think that would be all for today. We still have a few things to do. So for example, actually using the table redirects. And as always, if you've liked this type of content, hit like, subscribe, maybe tell a friend. And I'll see you next time. Fucking out.